This work is about comparing and combining interaction and eye tracking data for predicting user cognitive abilities in real time during visualization processing. And this is work done at the University of British Columbia. So information visualization are more and more prominent in our daily life, and we use them for a wide variety of tasks, which can include public engagement, checking disk usage, analyzing social networks, and a lot more things. However, there is very strong evidence that the cognitive abilities of the user can strongly impact how effectively and confidently they can process visualization. And this has been shown, for instance, for perceptual speed, working memory, and a few more abilities. And there's also evidence that eye tracking can be used to predict some of those cognitive abilities in real time during interaction or processing of a visualization. So altogether, those two findings show that there is potential for designing intelligent user adaptive visualization that can first detect at runtime the level of cognitive abilities of the user, and second, provide the user with a more personalized or adaptive interaction to facilitate visualization processing. However, such prediction of cognitive abilities has been limited so far to the simple settings shown on these pictures, namely one bar or radar graph and some fictional question answering tasks that does not really mimic how users use visualization in their daily life. So we wanted to extend this type of work in two different ways. First, by using a more realistic settings, namely by using MetroQuest, which is a commercial platform for public engagement widely used in North America that I will describe soon. And second, by using interaction data in addition to eye tracking data to perform such prediction. First, to understand if this can improve the accuracy of the prediction, and second, to understand if an eye tracker is required at all to perform such prediction of cognitive abilities. So MetroQuest is typically used to educate public about urban scenarios, and in this particular study we use a MetroQuest interface shown in this screen. Namely, users were provided with a map and deviation charts to compare three different public transit scenarios, and these transit scenarios are actually currently studied by the city of Vancouver. So this is a real project. This is widely covered by the news, so people know about it. And all of the data shown in the maps and the deviation charts are actually real data published by the city. And in addition, the 166 participants recruited for this study were all belonging to the community directly affected by the public scenario, so they are likely to care about the data shown in MetroQuest. So in the study, we first tested the cognitive abilities of the users, and then we let them interact with MetroQuest as much as they want and with no training to explore and read the different public transit scenario. So this is exactly how MetroQuest is used in real life. And we track the gaze of the users using a Tobii T120 eye tracker. And afterward, we assess the experience of the user with MetroQuest using interviews and questionnaires. So in the first round of the evaluation, we actually found that 4 different cognitive abilities significantly impacted how users process MetroQuest and their experience with the system, and they are listed on this slide. So the first is perceptual speed at performing simple visual tasks. Second is visual working memory to store visual information. Same for spatial memory, storing spatial information, and finally visual scanning, the speed at locating objects in our surroundings. And so some of the results we found, for instance, and this is just an example, so there's more in the paper, is that high visual working memory users did prefer the chart over the map, and they found the map difficult to process. So these users may need some help or personalized interaction to process the map in a more effective and confident way. And then we also found, for instance, that people with a lower perceptual speed made fewer comparisons of the different public transit scenario, although it's an important part of the MetroQuest system. So these users may need more hints or cues to perform such comparison. So altogether, what we want to do in this work is to predict these 4 user cognitive abilities in real time to see whether we can actually enable the type of intelligent support I just described. So to do so, we defined the prediction as binary classification tasks, namely for each of the 4 cognitive abilities, we split users into a high or low group, depending on the level of the cognitive abilities, and we use a median split to do so. And now to classify users into high or low, we use the set of features generated over the eye tracking and the interaction data, and those features are meant to capture the overall activity of the user and their attention to specific areas or interactive features of the interface. And we also use the combined feature set that just basically is a combination of both eye tracking and interaction features. And we train random forest classifiers with 25 random forest cross validation to predict each of the cognitive abilities. So this is the high level overview of the settings, and it is described in much more details in the paper. So some example of main results we found are shown on these slides. So we have the 4 charts, one for each of the 4 cognitive abilities. So on the chart, the x-axis is called window length, and this is meant to capture how much data is used to actually train and make the prediction of the cognitive abilities. So for instance, at window 10, we use only the first 10% of the interaction to make the prediction, and at window 100, we use the entire interaction. So this is to know how soon we can make prediction in the task during interaction with MetroQuest. And then the y-axis is the prediction accuracy. So the horizontal brown line is a majority class baseline, and then the other lines are the accuracy of the random forest classifiers for each of the combined feature set, eye tracking feature set, and interaction feature set. So some of the findings we found in particular is that eye tracking was still found to be better for 3 of the 4 cognitive abilities, where you see the red targets, so perceptual speed, spatial memory, and visual working memory. And in addition, the combined classifiers were not actually more accurate than eye tracking alone. So this tends to show that an eye tracker is still required to make a prediction for most of our cognitive abilities. This said, the interaction classifiers was still found to be very promising for visual scanning at the bottom left, because it can make very accurate prediction at the very first window, which is very promising. And in general, we still found that the interaction classifiers were more accurate overall than the majority class baseline, which still show that there's potential of interaction data to predict cognitive abilities with possibly a bit more research. Another important finding we found is that very early prediction is possible for 3 cognitive abilities, where you see the red target again. So right at window 10% for perceptual speed and visual scanning, and 30% for visual working memory. So this is very promising, because the sooner we can make prediction of the user cognitive abilities, the sooner we can provide them with more personalized or adaptive support or interaction. And even for the last ability, spatial memory, we can still make accurate prediction halfway in the task, which still leaves some time to provide personalized support. So this is an overview of our results, and there is more in the paper, including a strong discussion about the interpretability of the classifiers. But to conclude, we showed in this work that different cognitive abilities that are known to impact visualization processes can be predicted from both eye tracking and interaction data. Also, we still found that eye tracking tends to be more accurate overall on most of the target cognitive abilities. But still, interaction data can be promising for some specific abilities and has some value, and with the added value that there is no need for an extra device to track gaze. Altogether, all this work extended previous results that were found in more simpler settings and tasks with different visualization and cognitive abilities. So we show that prediction of cognitive abilities is possible in more realistic settings, where we use MetroQuest, which is a real system using real data and visualization. And so altogether, this contributes to the fact that showing that it is possible to design intelligent user adaptive visualization. And as a matter of fact, our current work is to study how we can design some form of adaptive support in MetroQuest by using our classifiers in real time to recognize the level of cognitive ability of the users and provide them with adaptive support in real time. Thank you for watching.